Good morning everyone. I am K. Narsimurthy, presently working as an assistant professor in the government first grade women's college Tumkur. This is my 28th video for the second semester BSc students of the Tumkur University, and the subject which I am teaching now is the physics, and the topic which I am teaching here is the self-inductance and the mutual inductance. This self-inductance and mutual inductance will comes in the chapter Electromagnetic Induction. It's a very small chapter which is kept in the second unit. There, when we about to start an electromagnetic induction, you have learnt in my previous video about the laws of electromagnetic induction, and those are the Faraday's law and the Lenz's law. Faraday's first law of electromagnetic induction, which tells you that whenever there is a change in the magnetic flux linked with a coil, an EMF is induced and current is induced, and this EMF is known as induced EMF, and this current is known as induced current. So EMF is induced as long as there is a change in the magnetic flux. When change in the magnetic flux stops, the EMF induced will also be stopped. This is what the Faraday's first law of electromagnetic induction. When we go to the second law of electromagnetic induction, means the Faraday's second law, it tells that the EMF induced is equal to the rate of change of magnetic flux. EMF is equal to the rate of change of magnetic flux. E is equal to d phi by dt. And the Lenz's law will gives us the direction of induced current. It states that the current is induced in a coil in such a way that it opposes the cause for the production. The induced current opposes the change in the magnetic flux. Therefore, I have to mention EMF equation E equals to minus d phi by dt. The minus will clearly indicate that it opposes the change in the magnetic flux. Now, after knowing the three laws, two Faraday's laws and one Lenz's law about this electromagnetic induction, I will start with the expression for the mutual inductance. In my previous video, I have derived an equation for the self-inductance. Now today I am going to derive an equation for the mutual inductance. Now mutual means you need to have two coils. So one coil C1 having n number of turns, which is connected to the galvanometer G to know the current flowing in it by just knowing the deflection of galvanometer. Another coil C2 having N2 number of turns is connected to the battery with a plug key. When plug key is closed, the current I2 will flow through the coil C2. Okay, and I'll take this phi 1 as the flux linked with the coil C1 due to the current I2 passing through the coil C2. See the thing here, the current is flowing in coil C2. It produces a magnetic field around it. Therefore, the flux linked with the coil C1 will change. Therefore, the induced current will flow in a coil C1. Now, the flux due to the coil C1, flux linked with the coil C1 due to current in another coil C2, current I2 in another coil C2 is what I am defining as phi 1. Phi 1 is the flux linked with the coil C1 due to the current I2 in a coil C2. Right. After defining this, now what I'll say here is the flux is proportional to the current. So if current increases, the flux will also increase. Flux will also increase in the coil C1. If current in the another coil C2 will increase, flux which is linked to the coil C1 will increase. If current in a coil C2 will decrease, that means to say flux linked with the coil C1 will decrease. So anyhow I can say that the flux which is linked to the coil C1 is directly proportional to the current which is flowing in another coil C2. So phi 1 is proportional to I2. It is not only the flux with the number of turns with single turn, it is the flux. So I need to consider the flux which is due to n number of turns. So I can take n1 into phi1 is proportional to I2. Now n1 into phi1 is equal to mi2. I have to add some constant to remove the proportionality symbol. So I have added a relevant constant m, which is called the mutual inductance of the coil C1 with respect to the coil C2. It is the mutual inductance of coil C1 with respect to the coil C2, or I can say that the coefficient of mutual induction. Right. Next, I am looking for the rate of change of magnetic flux which is linked with the coil C1, and it is due to the current I2 which is passing in the coil C2. If I have to see that, I need to integrate this equation. Look at this equation. N1 phi1 is equal to mi2. I am differentiating that equation. So N1 d phi 1 by dt is equal to m into di2 by dt. I have differentiated the previous equation with respect to time. So as I know, the number of turns in the coil C1 N1 is a constant with respect to time. It will not change with respect to time. So you need not differentiate N1. You take out the N1 out of this differentiation. Now phi1 is the flux which will change with time. So I have to differentiate that. So d phi1 by dt. Again, m mutual inductance is a constant. I told you m you have to take out of the differentiation, and I2 is the current which keep on changing with time. You have to differentiate I2 with respect to time. So only two variables which with respect to time are flux and current. So phi1 and I2, you need to differentiate those two. So therefore N1 d phi1 by dt is equal to m into di2 by dt. I am calling it as equation 1. So I got equation 1 just by differentiating the previous equation with respect to time. So what I got here is the rate of change of magnetic flux linked with a coil C1 due to the current I2 passing in the coil C2. I got equation 1. After that, let me move forward. I know this Faraday's second law and as well as the Lenz law. Faraday's second law tells you that EMF induced in a coil C1 is equal to rate of change of magnetic flux. So E is equal to N1 into d phi1 by dt. Please make a note here, I am putting the negative sign. This negative sign clearly indicates that this EMF induced is opposite to the change in the magnetic flux, because it is governed by the Lenz law. As Lenz law says, the EMF induced or current induced will oppose the change in the magnetic flux which is linked with the coil C1. So change in the magnetic flux is d phi1 by dt. So therefore I am writing EMF as minus N1 d phi1 by dt. Okay, it is clear. This equation I have written by considering Faraday's second law and the Lenz law. Both the laws, the minus is because of Lenz law, and N1 d phi by dt is from the Faraday's second law, which tells you EMF is equal to the rate of change of magnetic flux. Now this implies that N1 d phi1 by dt is equal to minus E. Just I am sending the minus other side. So N1 d phi 1 by dt is equal to minus E. I am calling this as equation 2. So I got equation 2. Let me move further. Substituting equation 2 in equation 1. So I am substituting this equation 2 and equation 1. See, the left hand side of equation 1 and equation 2 is same. So therefore I can easily equate the right hand side of these two equations. So right hand side here is, then the equation 1 is m di2 by dt, and right hand side of this equation 2 is minus E. If I equate these two, because left hand side of both the equations are same, so I can equate the right hand side of both the equations. Now it becomes minus E is equal to m di2 by dt. Now which implies that I am sending the minus sign to the right hand side. So EMF induced E is equal to minus m into di2 by dt. So if I only take the magnitude of induced EMF, I need not to bother about the direction. I need not to bother about the minus sign here. So I have taken the modulus of that. So minus sign here I need not mention because I am writing only the magnitude of induced EMF. So E is equal to minus di2 by dt. So from this equation, if I rearrange and get an equation for the mutual inductance, M is equal to E divided by di2 by dt. So I got an equation for the mutual inductance as M is equal to E divided by di2 by dt. E is what the EMF induced in the coil C1. I2 is what the current which is flowing in the coil C2. Now I can define the mutual inductance in this way. If I take di2 by dt as 1 amperes per second, if I take the denominator as 1 ampere per second, then M is equal to E. M is the mutual inductance, E is the EMF, di2 by dt is the rate of change of current which is flowing in an coil C2. Now I will define the mutual inductance between the two coils as EMF induced in one coil when current changes at a rate of 1 ampere per second in the neighboring coil. We have two coils, one is C1, another one is C2. The mutual inductance is numerically equal to the EMF induced in one coil due to the change in the current rate, due to the current changes at the rate of 1 ampere per second in the neighboring coil. If current changes 1 ampere per second in the neighboring coil, whatever will be the EMF induced in this coil C1 will be the mutual inductance. So mutual inductance as mentioned with the unit Henry, SI unit is Henry. After deriving an equation for mutual inductance, let us go for one more important derivation, which is expression for energy stored in an inductor. Now inductor is nothing but a coil. Inductor is nothing but a coil which is wound on some frame. Okay. Now consider a coil of self-inductance L. This coil of self-inductance L is connected to the battery as shown in the figure. Okay. Now what happens here is, because of the battery, the current flows in the circuit. When current flows in the circuit, the magnetic field will set up around this. When there is a change in the magnetic flux, linked with this coil, therefore, and current is induced in the same coil. This induced current will opposes the change in the current in the coil. It is what the current which is producing the induced current. It is what the change in current which is producing the induced current. Therefore, this induced EMF will definitely oppose the change in the current in the coil. Now, according to the Lenz's law, I can say this work done in developing the current. What must be the work done in developing the current in the circuit for a small interval of time dt? So you need to do the work against this back EMF to establish the current in the circuit. So what is the value of back EMF? The back EMF is E. E is the induced EMF which is developed in the coil. So you need to do the work against this EMF to establish the current in a coil for a small interval of time dt. So it is the EMF and you need to establish the current I. So it is multiplied by I, and for how long? So it is for a small interval of time dt, it has to be multiplied with the dt. So work done in establishing the current I against the back EMF for a short interval of time dt, therefore it is ei dt. The three things multiplied here will give us the work done, and that too it says very small work done dw, establishing the current for a small interval of time dt. I am looking for a very small work done, and I'll extend this to a full work done w. Okay, right. Now I know that the magnitude of induced EMF E is equal to L into di by dt. This is what the equation which I derived in my previous video. While doing the derivation of self-inductance, I have derived this equation, E is equal to L into di by dt. Let's call it as equation 2. Now this equation 2 which I got, the EMF equation, I am substituting in the equation 1. I am substituting equation 2 in equation 1. I got this work done equation as dw is equal to E. Instead of E, I am writing L into di by dt. Instead of induced EMF, I am writing L into di by dt. So multiplied by the current I and the dt. I dt will remain same. Now dw is equal to dt will cancels. So dw is equal to Li into di. I got the small work done, dw is equal to Li into di. This is the very small work done for a short interval of time dt. If I want to calculate the full work done for a whole time t, then I need to integrate this. So total work done is establish the current I through the coil is simply integral of dw. So total work done w is equal to integral of Li into di. Okay, so total work done is equal to, what will be the integral of I di? It is the only variable, I is the only variable, L is a constant which is self-inductance. I can take out this L out of this integral. So only the variable is I into di. So therefore if I integrate this I, it will be I square by 2. So W is equal to L into I square by 2. So if I rearrange and write this equation, W is equal to half L I square. This is the equation for the work done in establishing the current I in a coil against to the back EMF. So this has to be done, the work has to be done to further establish the current in the circuit. Okay, so this is the work done again, which is stored as a magnetic energy. So this work done is stored as an energy in the form of magnetic field. Okay, so therefore this energy, you can say work or an energy, everything is same, because this work done will what is actually storing as an magnetic field, or what is actually an energy in the form of magnetic field. So therefore I can write a same equation for energy. E is equal to half L I square. This is what the work done in establishing the current. This is what the energy which is stored in the form of magnetic field. So I have done the two important derivations today. One is the expression for mutual inductance. Another one is the energy stored in the coil. Okay. These two derivations are done using the Faraday's law as well as Lenz's law. The very famous law. For doing all these derivations, you need to be well versed in these Faraday's two laws and the Lenz's law. You need to learn these three important laws to do these derivations. Okay, these are some of the books which I referred. So Griffiths is a little bit standard book. You go through it, and these two are the written by Tumkur University faculties. And one more important book is Bridgelal and Subramaniam. It's about electrodynamics. You go through these books and the concept you will understand better. Thank you very much.